All right, so Monte Carlo simulation, just by a show of hands, how many people already know what that is and has already done some Monte Carlo simulation? Okay, so you probably know that this is not what I had in mind, right? This is Monte Carlo, and the name comes from the fact that this happens to be a really fun place for gamblers, particularly high rollers like James Bond and other characters. And the name Monte Carlo is probably the most fun aspect of it. It may seem kind of boring to you, but it turns out it's an incredibly powerful tool for simulating randomness in lots of different contexts. So we went through decision trees, and we know that if you've got binary outcomes, you can actually model that very easily. What if you don't have binary outcomes? What if you don't know exactly what the efficacy of a particular drug is, or you don't know what the revenues are, and you want to model it as a broader kind of a random variable, like, say, a normal random variable, things that you're used to from your other courses. So what we want to do is to be able to develop a method for calculating the impact of randomness on our decisions, particularly as it relates to adjusted net present value. And we want to do that in a way that's going to be relatively straightforward, because you want to be able to communicate these results to your shareholders, investors, other stakeholders. So it's not enough just to come up with a really fancy tool. The fancy tool actually has to be easily interpretable. And so Monte Carlo simulation is just a fantastic way of capturing all of those things. So let me start by giving you the basic idea behind Monte Carlo simulation. It's very, very simple. You start off by identifying the things that are random, whether it's revenues, or drug efficacy, or the patient enrollment, whatever variable you don't know and which matters to your adjusted net present value, you begin by modeling those things as random variables. So you pick a distribution like normal, log normal, gamma, beta. You've got a whole host of distributions that I'm sure you've been exposed to by now. And after you propose a particular random variable, you then propose a decision rule as to how you're going to make various different choices as a function of that random variable. So for example, if it turns out your drug efficacy is greater than half a standard deviation after initial experimentation with animal models, at that point you will go ahead with IND filing. However, if it's not, you'll withdraw. And so that's an example of a decision rule that's a function of those random variables. Okay? After you do that, you're ready to go to town in terms of this Monte Carlo simulation. What you do is you roll the dice, as it were, or you draw an outcome of this random variable. And when you draw the outcome, you apply it to a particular set of decisions, and then you get a result. And the result could be, if I had this outcome and I made this decision, it turned really badly and I lost $20 million. Or it could be, I made $50 million. You'll get an outcome. The idea behind Monte Carlo simulation is you're going to do this many, many times. And as you do this many, many times, what you get is a distribution of your outcomes. And once you get that distribution, you can then do whatever you like. For example, you can calculate the mean. And the mean of the distribution is your expected adjusted net present value. And so you can make a decision based just on that. If it's positive, take the project. If it's negative, get rid of the project. But what you can do with Monte Carlo simulation that you can't do with just calculating the expected value is you can calculate all sorts of other statistics. Like, for example, what's the probability that I'll lose money on the deal? I don't know what the expected value is to start with, but once I calculate it, I'm not as concerned about that as I am of not losing any money. So what's the probability I'm going to lose money? You can answer that with Monte Carlo simulation, but you can't really do that with decision trees as easily. Or you might be able to ask the question, what's the range of upside to downside? What's the best case scenario and the worst case scenario? How far apart are they? And that's a sense of risk. How much risk are you taking if you actually engage in this kind of investment strategy? All of these things come for free from Monte Carlo simulation. So this is an incredibly powerful, flexible tool. And you can actually do this in Excel. You don't need to be a super duper hacker to be able to do this. Now, Excel can be a little cumbersome if you're going to do a lot of these simulations. So I'll show you examples where you might want to just do a few in Excel get a sense of what's going on, and then use a more powerful programming language and do 1 million simulations. And I mean that literally, 1 million simulations. People actually do 1 million simulations for reasons that I'll describe. All right, any questions about that? That's sort of the basic outline. And then I'm going to go through more formally and show you what's going on, use some notation, and then we're going to do an example together. Okay? So here's a pictorial depiction of exactly what it is that we're going to do. I've got time on the x-axis, and I've got the NPV of a particular investment on the vertical axis. And I'm going to start at a particular point in time, time 0. That's the beginning, right, where we have some initial condition for the investment that I'm going to make. And then I'm going to simulate a realization of the randomness that we've identified. And once I simulate a realization of the randomness, and I've got my decision rule of how I'm going to behave as a function of that randomness, that's going to give me the NPV of my very, very first path. So if you think about, phase 1, phase 2, phase 3, and if I decide to go ahead or not go ahead, if you just simply run that kind of randomness through this process, at the end of it, you'll get, this is your NPV. Okay? Any questions about that? Okay. So that's one draw of my random distribution. Now I'm going to do it again. That's my second draw. I'm going to re-roll the dice. And now I'm going to simulate whether or not I go from phase 1 to phase 2 to phase 3, whether or not I have toxicity effects, all of the kinds of things that you don't know in advance, but you're modeling with certain kinds of random variables, you're going to get that. And then NP3, 4, 5. Some paths are really crazy, but that's the point of doing these simulations. You may get some really weird results. After you get all of these results, you see what I'm doing is I'm collecting a whole bunch of NPVs. And that's the output of a Monte Carlo simulation. It's these numbers here that you really care about, because you can average them to get an average NPV, and you can also look at how big the spread is. For example, this spread looks actually pretty big. I haven't given you any scale yet, so you can't really tell, but it sort of just looks really wild. If I had all of these lines right up against each other, you might feel a little bit more confident in making a decision based on this process. Right now, based upon these simulations, it looks like anything can happen. And that in and of itself is information. It's telling you that the randomness that you asserted for modeling each of the intermediate points where you have to make decisions, that randomness really has a big impact on your final bottom line. So now let me translate this into mathematical notation, and then we're going to actually apply this and see how it works. So suppose we model a project as a sequence of cash flows, but these cash flows are going to be random. They're random. We don't know what they are. They depend on your decision as well as on some underlying state variable, right? And so that's why I write these cash flows as a function of two other variables, y and z. Y are variables that you actually choose. You control y. Those are the decision variables. And z are the states of nature, whether or not your drug gets approved, whether or not you reach your endpoints, whether or not you've got toxicity effects, and so on. And so once you write it this way, you can show that your risk-adjusted NPV is going to simply be a function of the sequence of decisions that you make, as well as the sequence of the state variables, the y's and the z's, okay? It's a sequence. So in order to simulate a single sample path, you have to actually draw a bunch of different random variables, z0, z1, z2, all the way up to time t. And then you have to use your rule of thumb or your decision rule that says, if I get a z0, I'm going to choose y0. If I get a z1, I'm going to choose y1, so on and so forth, okay? So the idea behind a Monte Carlo simulation is to run a bunch of these random variables and then calculate what your decisions would have been given the realizations of those random variables, calculate the consequences of those decisions to get your risk-adjusted NPV, and then rinse and repeat and do this a lot, okay? So sample path 1 by sample path, I mean one sequence of random variables for a given draw. That's what we're doing, is basically pulling an entire path of history out of a hat. So this is one historical path. Let's say you got approved in phase 1, you succeeded phase 2, but at phase 3 you failed. That's one realization. The second realization is you succeeded in phase 1, but you got stopped in phase 2. The third realization is you succeeded phase 1, phase 2, phase 3, and you got approved, but the market tanked and you didn't really do well in your revenues, and so on and so forth, right? Each of these sequences gives you a different replay of history. And so after you calculate all of the consequences of those histories, you've now got a collection of M, realized, risk-adjusted, net present value. And these M RNPVs are your distribution that you can do with whatever you will. So given these realizations, you can calculate the expected value, in other words, the average. You can calculate the standard deviation. You can calculate the minimum, the maximum, all sorts of statistics. But this is really what you're looking for from the simulations. And when you calculate the expected value or the standard deviation, you can then make decisions based upon that.